This section is an introduction to the derivative. Starting with this graph of the function f in blue, what we see here is we have a point at c comma f of c, another point at c plus delta x comma f of c plus delta x. The green line is a secant line. It crosses the function in two places, and that is the slope of that's the slope between these 2 points, and that's an average rate of change between these 2 points. It's a slope, so it's a rise over run. The rise is this distance, f of c plus delta x minus f of c. And the run is from c to c plus delta x, so the run is delta x. That's an average rate of change. Now the derivative is an instantaneous rate of change. So the derivative would be, say, the slope of the tangent line at this specific point. So not a secant line, but the slope of the tangent line at this point. So what we want to do then is to imagine these points are approaching each other. So we have these 2 points over here and up here, and we allow them to approach each other so that the secant line becomes the tangent line. Let's take a look at that again. There's the 2 points, and the secant line approaches the tangent line. Now, a problem with this, of course, is that as we let the points go together, delta x goes to 0. We have 0 divided by 0. Of course, this is why we studied limits first. So we don't just imagine delta x is 0. We take a limit as delta x approaches 0 of this f of c plus delta x minus f of c over delta x, and that is equal to our derivative f prime of c. So this is finding the derivative at a specific value, but you can also find the derivative as a function. So over here in the textbook, this is what I call the limit definition of the derivative, f prime of x. The derivative as a function of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x, assuming the limit exists, and we'll talk a moment about that. Here's some notation for derivatives. F prime of x, dy dx, this is the Leibniz notation. Y prime, d dx of f of x, dx of y, this is a notation you'll get to more multivariable calculus. So a couple examples now of finding derivatives using this definition. Again, derivatives are slopes of tangent lines, they're rates of change. So finding the derivative of x cubed plus 2x. Here's our limit definition of the derivative. F of x is x cubed plus 2x. So therefore f of x plus delta x means wherever you see an x, put an x plus delta x. So x plus delta x cubed plus 2 times x plus delta x. And then minus f of x, so minus x cubed plus 2x. Multiply this all out. Distribute the 2. Lots of stuff cancels. Cancel out some dx's. Finally, you get down here where you can evaluate the limit, and the derivative is 3x squared plus 2. So this tells you that if you want to find the slope of a tangent line anywhere on this function, you plug in the x value here, and that will tell you the slope. Here's another example. Here we have the function y equals rad x. Here it is. So we're going to find the derivative at points 1, 1, 4, 2, and see what's going on at 0, 0. Here's the limit definition of the derivative. So f of x is rad x, f of x plus delta x is rad x plus delta x. To evaluate this limit, we've got to multiply top and bottom by the conjugate of the top. So difference of 2 squares gives us this expression. We can cancel x's, then we can cancel delta x's, which then allows us to evaluate this limit. As delta x goes to 0, we have 1 over rad x plus rad x, so 1 over 2 rad x. So then if we want to find the slope at 1, 1, we plug in 1 and we get 1/2. So the slope of this tangent line over here is 1/2, this blue one. The slope at 4, 2, we plug in 4, and the slope over here would be 1/4. As far as what's going on at 0, 0, it turns out that actually it's a vertical tangent line. Things are going up infinitely fast at that moment. And so we'll go back to the notes here for just a moment to discuss the idea of differentiability and continuity. Differentiability implies continuity, but not vice versa. So if you have a function which is differentiable, that is, the derivative exists, that limit exists, then it's going to look smooth. Polynomials are always differentiable. They're smooth everywhere. Sinusoids are that way as well. But this doesn't work in reverse. Just because you're continuous doesn't mean you're differentiable. So in this function, this is continuous everywhere, but we have these kinks, sharp turns. We have cusps, which is another type of sharp turn where the derivative is becoming infinite. And we also have a vertical tangent line where the derivative doesn't exist because the slope is undefined. So these are examples of places that are continuous and yet not differentiable. We can also look at derivatives not just in terms of finding the derivative by using from a function, but also an approximation of a derivative from table data. and this is using the idea of what's called a difference quotient. So there's three types of difference quotients. There's forward, backward, and symmetric. And the idea is it's called a difference quotient because slopes, in fact, are difference quotients. The slope, which, remember, derivatives are slopes, y2 minus y1 over x2 minus x1. So in its most basic form, you have differences with a quotient. So if you want to find approximations of f prime of 65 using these different difference quotients, here's 65, and so we assume the idea would be this is a differentiable function. We don't know what's going on between all these points. We know it's differentiable. So the forward difference quotient would be going forward in x, so we would use these two values. So on top it's 12 minus 8, on the bottom 80 minus 65. The backward difference quotient would be going backward along x, so it would be these 2 points here. So that's 8 minus 9 over 65 minus 45. And the symmetric difference quotient is going in both directions. So you use the outer points, 12 minus 9 over 80 minus 45. Those are the difference quotients. Here's another example of finding the derivative using the limit definition of the derivative. So we've got f of t is 3t minus t squared. We want to find the derivative at the point 0, 0 at the origin. So in terms of t, here's our limit definition of the derivative. So f of t plus delta t is 3t plus delta t minus t plus delta t squared, and then minus f of t, so minus 3t minus t squared. We distribute the 3, we multiply out t plus delta t squared, we cancel all sorts of things, the t squareds, the 3t's, we get down to here. Now we can cancel the delta t, delta t, delta t, get to here. Then you can evaluate the limit, and you get 3 minus 2t. So if we want to find the derivative at 0, 0, we plug in 0 for t. 3 minus 2 times 0 is 3, so the slope at the origin is 3. Now looking at the calculator, we can examine this as well. So what I've done is put in y equals 3x minus x squared as opposed to 3t minus t squared. I've got 3x minus x squared. And so here's a graph of it. So first, just graphically, you can do second calc and go down to dy dx, because that's, of course, our one version of our derivative notation we can use. And we can just type in 0 and press enter, and it tells us dy dx is 3. Now, another thing that's useful in a lot of contexts, let's go out to the home screen, is I do math, and I go to number 8 is nderiv. Nderiv takes 3 arguments. So I want to, first, what do I want to differentiate? Vars, y vars function y1 with respect to what variable? That would be x. And where do you want to find the derivative? At 0. So again, what do you want to differentiate with respect to what variable? Where do you want to find the derivative? You press enter, and you get 3 again. I can also use nderiv to graph. I can come over here, math 8, and I can put in y1, and then comma x. But then instead of a value, I do comma x again, and now it's going to graph the derivative. So when I graph this, I should get a graph of 3 minus 2t with that original parabola. And so here's the parabola, and then here comes 3 minus 2t. So you can also graph derivatives, and we'll talk later about how the graph of a function relates to the graph of a derivative.